Hello friends, in this video we're going to be talking about mole ratios. So you might have been thinking, so we've balanced this chemical equation, now what? Well, in this video we're going to talk about what we can use those coefficients in the balanced chemical equation to do. For our example reaction in this video, we're going to use the reaction of N2 and H2 to produce NH3 or ammonia. Now, the way this chemical equation is written now, it's not balanced. So let's go ahead and take care of that and we'll balance it. So 1 N2 reacts with 3 H2s to give us 2 NH3s. This is our balanced equation. Now let's talk about what those numbers mean. That means that 1 N2 reacts with 3 H2s to produce 2 NH3s. If this reaction were to happen a single time, 1 N2 would react with 3 H2s to produce 2 NH3s, or we would have a 1 to 3 to 2 ratio of those chemical species. So what if this reaction were to happen 2 times? Well, 2 N2s would react with 6 H2s to give us 4 NH3s. And if we look at the ratio of that, that means that we have a 2 to 6 to 4 ratio, which reduces to 1 to 3 to 2. Well, what if this reaction happened 100 times? Well, that means that we would have 100 N2s reacting with 300 H2s, giving us 200 NH3s. And again, that ratio, 100 to 300 to 200, would reduce to 1 to 3 to 2. What about an even bigger number? How about 6.022 times 10 to the 23rd reactions? Well, we would have 6.022 times 10 to the 23rd N2s reacting with 3 times that, which is 1.8 times 10 to the 24 H2s, to give us 2 times that, which is 1.2 times 10 to the 24 NH3s. And again, if we think about the ratio, 6.022 times 10 to the 23rd to 1.8 to 1.2, it'll reduce to 1 to 3 to 2. Now, once we're thinking about quantities of N2 and H2 and NH3 of that size, it might be helpful to put it in terms of moles. So of course, 6.022 times 10 to the 23rd, that's 1 mole, 1.8 times 10 to the 24 is 2 mole, and 1.2 times 10 to the 24 is 3 moles. So again, we see the 1 to 3 to 2 ratio of the substances in this chemical equation. Now that ratio isn't a coincidence. A reaction will always occur in the ratio of the coefficients in its balanced chemical equation. We call that ratio the mole ratio because we can use it to relate mole quantities of those chemical substances in an equation. So for this particular reaction, the ratio is always 1 to 3 to 2. And this reaction has never happened not in a 1 to 3 to 2 ratio. Now for our purposes, we'll use the mole ratio as a conversion factor. So we're going to construct a conversion factor from the coefficients of a balanced chemical equation. And we can use that conversion factor to compare any mole amount of any 2 substances in a chemical equation. So let's look at our reaction again. So from this reaction, I could write a mole ratio comparing N2 to H2. So I would write that as 1 N2 over 3 H2s, or 3 H2 over 1 N2, right? Because we can write conversion factors either way. I could also write a conversion factor comparing N2 to NH3. So I would write 1 N2 over 2 NH3s, or 2 NH3 over 1 N2. And lastly, I could write a mole ratio between H2 and NH3. So 3 H2s over 2 NH3, or 2 NH3 over 3 H2s. The mole ratio that I'll use will depend on my calculation, but I'm going to think about H2 or NH3 as being the units in my conversion factor, and I'm going to use dimensional analysis. So let's look at an example. So how many moles of ammonia, or NH3, can be made from 9 moles of hydrogen gas, or H2? So first I'm going to need my balanced chemical equation. So we'll use the same equation we've been using this whole video. And I'm going to set this up just like any dimensional analysis problem. I've got 9 moles of H2. And I'm going to multiply that quantity by my conversion factor, or by the mole ratio. So the mole ratio I'm going to use is 2 NH3 over 3 H2. So notice that I'm using the coefficients from the balanced chemical equation to create this ratio. And I choose 2 NH3 over 3 H2 because, again, I'm thinking about H2 as being the unit, and I want to cancel those units out. So I need H2 on the bottom and NH3 on the top. So as I multiply, my units will cancel. I'll do 9 times 2, which is 18, divided by 3, which is 6. So I expect to make 6.00 moles of NH3. Okay, let's do another example with the same equation. So how many moles of nitrogen gas are needed to react completely with 10.5 moles of hydrogen gas? So again, I'm going to set this up just like any dimensional analysis problem. I'm going to take my 10.5 moles of H2. I'm going to multiply that by the mole ratio, and I'm going to set my mole ratio up as N2 over H2. So that's 1 N2 over 3 H2s. I'm using the coefficients from that balanced chemical equation to create that conversion factor. And I want H2 on the bottom because I want to think about canceling those H2s out as I multiply through here. So we're going to do 10.5 times 1 divided by 3. We might need to use our calculator for that, but if we punch that in, we get 3.50 moles of N2. And that is stoichiometry.